When a plane intersects a double-naped cone, the resulting intersection is called a conic section, or simply a conic. The angle of the plane determines the shape of the intersection. We will study 3 of these conics. The first conic we'll study is the ellipse, and the ellipse is formed when a plane intersects a double-naped cone in this way. The second conic we will study is the hyperbola. And the hyperbola is formed, it has 2 branches, and it's formed when a plane intersects a double-naped cone in this fashion. And the last one we'll study is the parabola, and the parabola is formed when a plane intersects a double-naped cone in this fashion. So we're going to focus in this video on the ellipse. An ellipse is the set of all points xy in a plane such that the sum of their distances from 2 fixed points is constant. Each fixed point is called a focus. Plural, it would be foci. To draw an ellipse, we can use thumbtacks to pin the ends of a string to a piece of paper, leaving some slack. The length of the string is the constant distance mentioned in the definition of the ellipse. The thumbtacks represents the foci of the ellipse. Trace a curve with the pencil held taut against the string, and the resulting curve will be an ellipse. Let's talk about the anatomy of an ellipse. Every ellipse has 2 axes of symmetry. The longer axis of symmetry is called the major axis, and the shorter axis of symmetry is called the minor axis. The center of an ellipse is the midpoint of both the major and the minor axis. So that's the center of the ellipse there. The axes are perpendicular at the center, so they form a 90-degree angle at that center intersection. Each endpoint of the major axis is a vertex of the ellipse. The vertexes together, plural, are called vertices. And each endpoint of the minor axis is called a covertex. So together they would be called covertices of the ellipse. The foci always lie on the major axis. So whatever the longest axis of symmetry is, that's where you'll find the foci of the ellipse. So now let's talk about the equation of an ellipse. So the standard form of the equation of an ellipse with a center at the point HK and with a major axis parallel to the x-axis is given by this equation, which is the fraction x minus h squared divided by a squared plus the fraction y minus k squared divided by b squared equal 1. So h and k, those values represent the center of the ellipse. So if you have x minus h, that value h is the x value of the center of the ellipse. And when you have y minus k, that value k is the y value of the center of the ellipse. The values a and b also play a role in the geometry of the ellipse. A is the distance from the center of the ellipse to both of the vertices. So the distance from this vertex to the center is a. The distance from the center to the other vertex is also a. The value b is the distance from the center to either covertex. So the distance from the center to this covertex is b. The distance from the center to this covertex is also b. There's another value that is not apparent in the equation, but it will give us the distance from the center to either of the foci. And that value is c. And the formula for c is that c squared is equal to a squared minus b squared. So if you know a and b, you can find the value of c. As a matter of fact, if you know any 2 of those lengths, you can find the other using this formula. Let's go ahead and graph an ellipse. Sketch a graph of the ellipse with this equation. X plus 3 squared over 49 plus y minus 2 squared over 9 is equal to 1. Let's match this up with the form of the equation that we just saw. X minus h squared over a squared plus y minus k squared over b squared equals 1. And let's identify the values of h, k, a, and b because they tell us a lot about the shape of the ellipse. Since the first term is x minus h, The only way I can have an x plus 3 here is if h is negative 3. That would be x minus negative 3. So h is negative 3. And here I have y minus k. And that means that k is 2 because we have here y minus 2. So I have that k is 2. So now I know where the center of the ellipse is. The center of the ellipse is at hk. And that central point hk is the point here, negative 3, 2. So I'll plot that point, negative 3, 2. All right, once you've plotted the point negative 3, 2, now we need to know how far the vertices are from that central point. So that's where we have to find the value of a. A is always the square root of the bigger of the two denominators. So since 49 is bigger than 9, a is the square root of 49. So a is equal to 7. That means that the distance from the center to both vertices is 7 units. So I'll go 7 units to the left and 7 units to the right of the center, and that's where I will have vertices of my ellipse. I also need to find where the co-vertices are. So I look at the smaller of the two numbers, and that's 9, and I take the square root. That'll tell me how far from the center the co-vertices are. So the square root of 9 is 3, so b is equal to 3. So from the center, I need to go in a perpendicular direction. I just went left and right to get to the vertices. And now I need to go up and down 3 units to get to the co-vertices. So I make a point 3 units up, because b is equal to 3, and a point 3 units down from the center. 1, 2, 3. And those are the vertices and co-vertices of the ellipse. So if I just connect those dots, that is the shape of my ellipse. Now the last thing I'd want to find is I'd want to find out where the foci are. And I have a and b, so I'm going to use the formula c squared equals a squared minus b squared to find the value of c. Well, a squared is 49, as we see. B squared is 9. So you subtract those, you get that c is equal to the square root of 40. And the square root of 40 is about 6.3. So from the center, I'm going to go 6.3 units to the right and 6.3 units to the left. Those red dots around the center, those are the foci. So now I've drawn the ellipse itself by identifying the vertices and co-vertices, but I've also graphed the points that are the foci of the ellipse. All right, let's take a look at coming up with the equation of an ellipse given the graph. So the directions say write an equation in standard form for the ellipse graphed below. So to find an equation, we have to identify the major and minor axis, and the endpoints of those will be the vertices and co-vertices, and then I just have to identify the intersection point of those axes to figure out where the center is. So the major axis is the longer of the two axes, and in this case you notice the major axis is vertical. The major axis in this case is parallel to the y-axis. The minor axis is this horizontal line segment here, and the intersection point of those two axes is going to be the center. So once we see the axis of symmetry, the vertical one, and the axis of symmetry, the horizontal one, wherever they intersect will be the center, and that'll be my value of hk. So h is the x value here, negative 3, and k is the y value, negative 2. So there I have the value of h and k. And in order to find the other two values I need, which are a and b, I just have to count how far the center is from the vertices and also how far the center is from the co-vertices. The distance from the center to that vertex on top is 1, 2, 3, 4. So the value of a is 4. The distance from the center to that co-vertex to the left of it is 1, 2. So that means the value of b is equal to 2. Now all I need to do is figure out which equation I should use. Well, here are my two choices. For a horizontal major axis, you'll notice the value of a, which is always the larger number, is in the denominator of the term that has the variable x in it. For a vertical major axis, you'll notice a, the larger of the two values, is in the denominator of the term that has the variable y in it. Because my major axis is vertical, the value of a, the square of the larger of these two distances, should be in the denominator of the term with y. So the plugging in of these values will into this vertical major axis equation will give me this. X minus h will be x minus negative 3 squared over b squared in this case is 2 squared, plus y minus k, which is y minus negative 2 squared, over a squared in this case is 4 squared. So cleaning this up a little bit, we know minus a negative is plus, 2 squared is 4, and 4 squared is 16. This is the standard form of the ellipse that was drawn, and that's all we need to know. We need to know where the major and minor axis intersect each other to find the center. We need to know how far the vertex is from any vertex from the center to find the value of a, and we need to know how far the co-vertex is from the center to find the value of b. And then we can determine which equation we're using by which orientation the major axis is. If the major axis is horizontal, we'll use this equation. If the major axis is vertical, we use this equation. All right, the last thing I want to look at here is, given the equation of a conic in this general form, I want to be able to put that conic in standard form. So here's the equation of a conic, and it says it is the equation of a conic. Write the standard form of the conic. In order to do this, we need to complete the square for both variables, x and y. To do that, I'm going to group the terms with the same variables and move the constant to the other side of the equation. So I'm grouping the x squared with the x, the y squared with the y, and I'm putting that 148 on the other side. So 36x squared plus 216x squared, I group those together. 16y squared minus 160y, I group those together. And that positive 148, I just subtracted from both sides. So now it's on the other side. Now I'm going to factor the coefficient of the quadratic term out of each pair. Well, in the first pair, 36x squared plus 16x, the quadratic term has a coefficient of 36, so I'm going to factor out a 36. And in the second pair, 16y squared minus 160y, the quadratic term has a coefficient of 16, so I'm factoring a 16 out of the second pair. So I factor a 36 out of the first pair, and this is what I have left inside of the parentheses. I factor a 16 out of the second pair, and this is what I'll have left inside of the parentheses. So now I have these binomials x squared plus 6x and y squared minus 10y. And what I'm going to do is I'm going to complete the perfect square trinomials with those binomials in each of those parentheses by adding an appropriate constant. For instance, in the first case, x squared plus 6x, the appropriate constant to add would be half of 6 squared. Half of 6 is 3, and 3 squared is 9. So inside of this first parenthesis, if I want a perfect square trinomial, I'd add 9. But adding a 9 inside of that parenthesis amounts to adding 9 times 36 on the left side of this equal sign. So in order to keep the equation balanced, I have to add 9 times 36 to the right side also. So that 9 that I'm adding in is multiplied by 36 on the outside of the parenthesis. So to keep the equation balanced, I add 9 times 36 to the other side. Now I'm going to do the same thing for y squared minus 10y. That binomial, if I add to it half of 10 squared, it'll be a perfect square trinomial. So half of 10 is 5, and 5 squared is 25. So I'm going to add 25 inside of this parenthesis. Adding 25 inside of that parenthesis is really adding 25 times 16 to the left side of the equal sign. So to keep it balanced, I'm going to add 25 times 16 to the right side of the equal sign also. Now I have these two perfect square trinomials inside of the parentheses. I'm going to factor those perfect square trinomials and just combine the like terms on the right side. So factoring x squared plus 6x plus 9 gives me x plus 3 squared. Factoring y squared minus 10y plus 25 gives me y minus 5 squared. And combining all those terms on the right hand side gives me 576. So I get this new equation. And the last step in this equation to put it in standard form of an ellipse is to divide all three of these terms by 576. If I divide this by 576, I'll get x plus 3 squared over 16. If I divide this by 576, I'll get y minus 5 squared over 36. And if I divide 576 by 576, I'll just get 1. This is the standard form of the ellipse that had this original form. And that's how we go from the general form to the standard form of a conic.